Okay, we start with uh, our lecture. We continue with this introduction, the performance and failure criteria. Obviously, we know that pavements are designed to fail, and we we get this idea when it fails is how it performs. The performance measurement is very easy. When you feel that the road is not good enough to get a good riding surface, your comfort level is decreased, and the speed in which you intend to drive is not attainable, not due to the congestion but due to the pavement condition. Sometimes you cannot attain speed required or desired or posted speed because of some sharp curve. So obviously the speed is less there, but we are not talking about the geometrical failure of this pavement. We are talking about the structural or functional failure of the pavement. Structural means either the road has been broken or it has been settled at some places or at many places. And functional means when you want to attain the speed because of that damaged road or because of the less skidding effect, you cannot ride on the surface as would you like. So that's what we call the functional and structural failure, and that is where the point is measured, where you feel that the road is to be repaired or it has start performing, it has stopped performing. Now this is the failure mechanism. The pavement fail because of fatigue and rutting. Fatigue means the number of repetition of the load that has been being applied to this pavement has reached its ultimate, and any more repetition, and if you continue with those repetition of the traffic, the pavement is not going to survive and it will crack at different places. While rutting is the depression caused by the excessive wheel loading of a heavy vehicle, and you will see the channels along the wheel path, especially on the lane that is occupying, that is meant for heavy vehicle. So it can be a left lane, extreme left lane, if you are, on the left hand, right hand drive system, and if you are in the environment where left hand drive system, then it will be the extreme right lane, where where the trucks or the vehicles are meant for riding all the time. So what happens is that there there are strains. Why, how we call the pavement has damage, and how we know, what happens is that the vehicle, whenever the load is applied, the strain is caused, and strain is change in length per unit length. Obviously here we are talking about the change in depth per unit depth, right, in terms of, and obviously it's a unitless quantity. So if the strain in the pavement has gone beyond its limit, then the failure is caused. As we can see that the major cause of the pavement failure is due to fatigue and due to rutting. Fatigue is always measured at the bottom of the asphaltic layer. If you can recall the section of the flexible pavement, the first two layers are of an asphaltic course, and the other two layers of an unbounded aggregate, or maybe bounded unbounded aggregate or symmetrated base that is there. So for fatigue, you measured that fatigue strain at the bottom of the bituminous bound material, and this is a tensile strain, maximum tensile strain. And at the top of the subgrade, you measured a compressive strain that is a vertical in direction, and it is at the top of the subgrade. Now, imagine, now one of the query may be, one of the thing is that whether the strain, tensile strain and the compressive strain can be measured at the same place. The answer is yes. And what I mean is that if you have all the layers made of the asphalt concrete, then you, the end of this point, if imagine if this is also your bituminous bound material, then you will measure the tensile strain here, not at this point. So yes, in one type of the pavement, both compressive strain and tensile strain can be measured at the top of the subgrade. The following relationship is usually applied to calculate the permissible tensile and compressive strain, and by limiting strain criterion for 85% probability of survival of n repetition of 80 kilonewton, means 18 kilopound or 8 ton single axle load, and an equivalent pavement temperature of 20 degrees centigrade. What I mean to say, if your temperature is 25 degrees centigrade, or if your standard axle load is 12 ton, maybe, and most of the countries it is like that, this equation cannot be applied, because this is an equation that has been evaluated for the standard condition of 20 degrees centigrade and 8 ton allowed load on a single axle. So there is a different equation for fatigue and for the different equation for the subgrade. As we go ahead, if you want to design a pavement, there are two aspects of the design: the functional aspects and the structural aspect. When we say functional, safety and riding, and we say structure, how it is surviving the traffic load. How you measured structural performance? It is because of the strength evaluated whenever there is a truck passing over it. Functional performance, it's the skidding, it's the tire contact and the brake applied, especially by a car or pickup truck. And obviously, comfort is always for the motorist. So whenever they feel uncomfortable, for them the road has failed to meet its desired objectives. So there comes another definition. The pavement thickness design is the determination of required thickness of various pavement layers to protect a given soil condition for a given wheel load. What is the given wheel load? Is that if you have a tire pressure of 150 psi, at the bottom of the subgrade, it should be around 3 psi. If it is like this, it means that your pavement section is good enough. It is deep enough to survive this load of the traffic. And if it is not, then you have to increase the depth of the pavement. So that becomes 3 psi. This is actually, it depends on the soil condition, and it also depends upon how you have come of your design. It also depends what are the material used in various layer of the pavement. Again, 3 psi is a thumb rule, right? In a thumb rule, there may not be even evidence, but it is somehow it is accepted as a standard. It may not be uh, written standard, maybe a written standard, but the reference may be sometime missing. Or in this pretext, you can say that maybe I've calculated stress and doesn't out comes out to be 3 psi, that my pavement has been failed. Actually, not all the software do this. Although they got it, but we actually determine the failure in terms of whether it has reached its design life or not. So if it reaches design life, for example, if a pavement is designed for 20 years and the stress analysis comes out to be 22 years, it means the section is okay. But if your pavement is designed for 20 years and your calculations shows it, it is less than 20 years, then the pavement has failed. So what are the pavement design process? The pavement is oil or highly influenced by the climatic and environment condition. Climatic means the temperature, as well as you the rain, the moisture, and the moisture can be in form of the ice and snow as well. It's not always the rain, because ultimately that snow melts, and it is also the moisture that has to be resisted by the pavement. When when we say traffic, it means how many number of it and what is the load magnitude, because the numbers are important. I always maintain that if a Boeing 777 can land on the pavement in the NED, the pavement is not going to fail. But if it keep on landing every day, every night, then the pavement is going to fail. So the number of repetition is what the causes the failure. Because sometimes one of incident is okay, but it should not be regular. So that's why not only the load is important, but how much time it is being applied to your surface. And then comes the material property. In case of flexible pavement, the asphalt concrete that is being used, the aggregate base, and the subbase. And obviously, how good your soil is. So value of subgrade is also important. What type of the soil is? Is it a rocky? Is it a clay? So all will depend. This the performance will depend on all these factors as well. So when we design a pavement, we mean how much should be asphalt concrete for a given traffic in terms of load and magnitude, the climatic condition, and the type of material that is being used. So the only question mark is the thickness of various layers. And sometimes this also determines whether that extra layer can be needed or not. Sometimes you have asphalt concrete laying directly on the aggregate base. It means the load is very less, just like a shoulder, or maybe just a common type of road, a local road, maybe the roads within the rural areas connecting the the farmland. That can be one thing. Obviously, when you say base course and the sub base course, they are sometimes add as a synonym, because base and sub base is also an aggregate base, but it is of part of larger size aggregate, and it's, the value is lesser, because the concept is provide best material at the top of the layer, because the stress is maximum at that point, the tire is in contact, and as you gradually goes down, you can have a lesser material, because the load demand at that point is decreased. So truck, buses, and car. So we always know how much design life, how to where what time our pavement is going to last. This we are also known. We have this setup. This is our own known parameter when we are designing the pavement. The performance is what we desired, and the design life traffic is always we predict that this type of traffic will be occur, say around 20 years, after 20 years as well. So not only the present, actually the present traffic is being forecasted to the year of your pavement design, the design life. Before I move ahead, there is a simple thumb rule that you must remember. We don't design pavement for cars. We design pavement for trucks, mini trucks. Or in other words, any vehicle that has got more than 4 wheels or at least 6 wheels, we design a pavement for that. So if you come up with, say, some highest van that has got 4 tires, and that, it can carry, say, 16 or 17 people, that even there we don't design it, we don't consider it for the pavement thickness. We only design vehicle that has got more than at least 6 wheels for the pavement design. The question is why? There is a simple answer: because the cumulative load of those vehicles is not matter much. So instead of wasting your time, you don't um, consider in the design. Even if you consider a design, it is not going to impact much on your design. And for the if you are designing a geometry, then obviously sometimes the trucks may be considered for turning radii, but if you are designing a local road, then you consider car as your design vehicle. So for one of the difference maybe in not maybe, it's there. The difference between geometric design and the pavement design is that the design vehicle is different. For the pavement design, it is always a truck, but for the geometric design, it can be truck or it can be a car, depending upon the purpose of the road. Another difference between a geometric design and a pavement design is that geometric design, we design for the visible features of the surface. We always know and we always measure how much the lane width is. But if I ask you to measure the depth of the layer, you are not going to do it, except you are used before. You cannot do it by your eyes. You have to use some non-destructive testing equipments, or you have to damage the road, take the core out, then only you can define. So this another different, the pavement design and geometric design. So what do you mean by selected design life? Now if you look at in the other civil engineering structure, you don't say this building is designed for 100 years, or you don't design it considering the life of the structure. But this is not the case with with the with the pavement. Let's look at how we design our pavement. For the functional proper performance, we always mean ride quality. When the road is constructed, this is the point. It is performing at its best, a new road, but with time, this performance get deteriorated, and there is a time when we reach that something is to be done to improve this pavement. There becomes a rehabilitation technique, and then obviously, you know, you will have your curve started, and then it can deteriorate it. And when it gets the unacceptable limit, you say it has failed. So the pavement has got this 2 point you have, it's a design life. Similarly with the structure, you have this curve. This is what we call the terminal point, where you feel that your structure has failed, and then you rehabilitate it. Remember one thing more. If you compare the heights at the first performance and height of rehabilitation, there is always a difference. It's just like if you have, overhauled the car engine, it is not going to perform at its best. You have to, there is always a compromise. So this similarly, a rehabilitated pavement cannot replace the new pavement, or its performance maybe not be as good, even though it is a new layer. It's very logical. So that's why the second height will not reach the first height anyhow, either in functional point or the structural point. There is no replacement of the new thing, right? Then what we say about the predicted design traffic. It is a traffic characterized. Now, let's go back once again to that predicted traffic line. Is you have, you know this, what is the traffic at present, and then you have to use some parameters like growth rate, like some projection factors, and then you come up with this value. And again, this value may not be exactly if you measured at the end of the design life. The traffic you may have you projected for 15 years may have come along the road in 10 years. And that is where the fatigue comes out. Fatigue says the road is designed for this much of the traffic that you have projected, that you have predicted for 15 years of this, 10, 20 years of design life. But because of the socio-economical condition of the area, that the same amount of traffic that you have predicted for 20 years now has come in 15 years, and that is where the indication of fatigue cracking starts to develop. It is being shown or it is being witnessed. So this is the predicted design traffic, and no one can predict the future. I always say in a pavement design life, what happens in this on September, you all know what happens. And Pakistan were asked to open their road for the war on Afghanistan. At that time, the Torkham road was not designed for carrying the missiles and heavy war-like things, equipments. So the road that was expected to survive for another 5 years, because of the unpredicted traffic, it designed at the same moment. So obviously no one would thought that what would happen in the next 5 years. Sometimes, what happens that the truck, one type of truck becomes obsolete, and the other types with a different configuration come along. So again, the repetition is increased. So this what we can design. You cannot predict, the traffic for some times. And there are instances when you have predicted the traffic and it doesn't come around in 25 years because the socio-economic condition of that country has changed. For instance, nowadays we are going to this COVID breakdowns. Many countries have sealed their borders. So the highways that have been designed for that traffic is not being witnessed. So that is another prediction that has been made. The road seems to be over designed because of this pandemic. So these are the things the the engineer is always confronted. So if the pavement failed before your expected design life, it may be the reasons beyond the designer control. We want the pavement expert to have designed, because there are things that is beyond the control. It's not always that something bad has happened, people are taking more loads. It is there, one of the reason for failure is that, but it may not be the only reason. So that's why pavement may design fail before its design expected life. So, how you characterize the load? We talk about how many cars, pickup, buses, trucks, and trailers, 5 axle, 6 axle, sometimes now multiple axle trailers are also there. So, these are spectrum of traffic load. Traffic load varies from few pounds to more thousand pounds, from few tons to many tons, from 8 tons. For example, the car is 6 tons, and the truck, 3 axle trucks is in empty are 10 tons. Some trailers are say 20 tons. So it depends. Empty loaded. When it is fully loaded, it may be 40 tons, maybe 50 tons. So the load um, carrying capacity of the vehicle vary with different aspects. The amount of the thing that carries. It may be carrying a cement bag, or it may be carrying a cotton, depending upon the commodity it is carrying. The load may vary on the same type of the truck. 5 axle truck may have say 35 tons. Sometime a 5 axle truck may have a 40, 50 tons. The same truck that say the same water tanker that carries of the same size of water, the weight is different. It is carrying oil, the weight is different. So how we design the, what are the approaches to design a pavement? Uh, Actually, there are three approaches. There is an empirical approach, there is a mechanistic empirical approach, and nowadays it is a full mechanistic approach. So what is that uh, empirical, mechanistic, and the mechanistic empirical? The empirical approaches are derived from experience. In terms of in-service payment or test sections, people have constructed a test section that, and they are subjected to some loads, and obviously there are some constraints on it, and they come up with this. Okay, if you design a pavement like this on this type of the soil, these are the thicknesses, and based on their experiments. But there's a problem to it. If you have if constructed a road, say in in Balochistan, and you want to apply the same thing on the Karachi, or maybe on Islamabad, the problem is the environmental conditions vary. In Balochistan, we have a very dry climate. Most of the time, the rain doesn't occur. In Karachi, you have a moderate climate, and Islamabad, you always there is most of the time there is a rainy climate. So if you have designed a model at one place, you apply a model to other place, then you may have a problem, because this set of it is always dependent upon the set of the climatic condition, loading condition for which it was experimented. It can be interpolated, but it cannot be extrapolated. The point is that, remember, most of the time people won't go for the extrapolation in the pavement design, and that should be forbidden. It's a practice that should not be adopted. extrapolation is not allowed, interpolation is allowed. What I mean by extrapolation, interpolation. For example, if your pavement design method limit only 50 million of E cells and you have got 70 million E cells, don't use that method, because you never know what is beyond 50 millions, and what you also do not know whether the pavement design method you are applying valid for more than was tested for 60 million E cells or not. So then you may got it right, but you may got the wrong. The problem is nobody sees the right. People sees the wrong side. And when you ask them, you try to convince them, you see that people cannot convince. You cannot extrapolate. But if you have, say, example, for 50 million E cells, your pavement, your demand is 30 million E cells, design it. Because this is what we call interpolation. So interpolation is always allowed. Extrapolation is not allowed. And this is where I feel that even though I've not got enough research data, but I know that most of the road failures, one of the reasons is that it has been extrapolated for the design. So what we do, the point may be what we do if you have 70 million E cells, then at this case, the easiest way is to reduce your desired life. If you're projecting, say, traffic for 15 years, and that comes out to 70 millions. So what you do, you reduce your expected life, maybe say, not, if you cannot do it, go for 15 years, you can go for, say, 10 years, maybe 12 years. Or there is a technique what we call stage construction, that after 10 years I will go for another 5 years. This is also doable. But again, don't try to design a pavement for extrapolation. And if you have the methods, alternative method that can give you enough evidence for 200 million, more than 70 million, go for that. So that's what the bottom line is. Are accurate only for the exact condition for which they were developed, and may be invalid outside the range of the variables used in the development. AASHO procedure, road node procedure. And again, you see the limit of AASHO road node is 30 million. The limit of AASHO flexible is 50 million. So if you are trying to use road node method, and if your traffic comes out to be, say, 40 millions, don't use road node method, instead use AASHO procedure. But if your traffic comes out to be 60 millions, then in AASHO rigid method, you can have 100 million E cells. So instead of going for flexible pavement design, go for the rigid pavement design. But if your traffic is more than 100 million, this is the quiz that are being evidenced nowadays in Pakistan as well, then go for the lesser design life, right? So empirical methods, these methods are generally used to determine the required pavement thickness, the number of load repair applications required to cause failures, or the occurrence of distress due to pavement material properties, subgrade type, climate, and traffic conditions. One advantage in using empirical model is that they tend to simple and easy to use. Unfortunately, they are usually only accurate for the exact condition for which they have been developed. They may be invalid outside of the range of variables used in the development of the method. So what was AASHO road test conditions? The climate between -4 to 24 degrees centigrade, average precipitation 34 inches, average frost penetration depth 28 inch. Do any of this condition exist in Karachi? No. Normally, you know, how you do it? Because in in summer, you always keep your air condition to 16 degrees centigrade. Why? The temperature outside is normally 28-30 degrees centigrade. In Karachi, don't have -4 degrees centigrade. You know, we even if the temperature falls 10 degrees centigrade, we are all in our homes. And what is the average annual precipitation? 864? No, 240, 240 mm. So it is much more less. You know what happens this time is if what it falls for 270 mm for 3 hours this time, and you see all your infrastructure were in shambles. They were not designed for that, instant rate. And for for US 864 mm is normal. And then we don't have um, snow or something, so depth is 28 inches. And you know what? In Karachi, most of the design pavement is based on AASHO method. The main arterial, I mean. We don't design local roads. We design on the thumb rule. There are no valid method. There are, templates, and that is applied without any thinking. So for local, say arterials, for major arterials nowadays, express as well, expressway, motorways, we don't design, but we design with the AASHO method. With all the discussion we had uh, a little while ago, this seems to be very different that I'm presenting. Then the classification, they have taken this worst soil. Normally, we don't design or we don't recommend a pavement on that type of soil. We instead want to replace it, and we have some other fill material and go. But they have designed it so that poor condition, there's a poorly drained. So this is the point that that is good for Karachi. It matches with Karachi, that we don't have a drained, poorly drained pavement section most of the time. The strength is 2.4 CBR, but the soil of Karachi is very good. It's around 10 CBR most of the time, and it's even near the seashore. It gives you 6, 7. It's like in this range. This is the material we have, yes. Asphalt concrete, there is a layer coefficient that will be discussed because this is an introduction, so we'll discuss in later part of this course. Then there's a base course, crushed stone, and we have a very good crushed stone, by the way, in Pakistan. We don't have any problem with our crushed stone. There is even, there are, the resources are, mashallah, enough here. And the sub-base course, sandy gravel, again, this is no problem with this material. So we are very good at those materials. There is no point that we feel that these material cannot be have. But there are some countries in which they don't have even crush aggregate based course, and if it is there, they are not of good quality as we do have in our Pakistan. So the problem with AASHO is an empirical procedure applied to the AASHO road test condition under which it was developed. So if the model that is developed somewhere else, applied somewhere else, it always got the problem like we have. So mechanistic empirical procedure. Now it's uh, partly empirical and partly mechanistic. But let me define you what is mechanistic. Mechanistic means the stress and strain capability of the structure of the material. So if your stress and strain relation is okay, then this is a mechanistic thing. So in mechanistic, actually we evaluate the stress and strain of the pavement section and we come out with the solutions. Calculate stresses, strain and deflection induced by the traffic and the environmental conditions. Now, in empirical method in which distress models are used to predict the future performance of the pavement structure. The distress models are typically developed from the laboratory data and calibrated with the field data. Asphalt Institute procedure SHARP. This is a strategic highway research projects process It actually all started in 1987 or is now being developed. A special test performance is developed. Other things have been developed, and most of the thing has been modified to compensate for the unpredictable behavior of the asphalt pavement. The binder measurement, the asphalt that is being used, how its testing has been modified, and similarly, the other properties of aggregate that were conventionally used are also being modified. And the mixed design procedure, the way the proportions that are being also being modified with this SHRP. Most of the countries other than USA may not have this facility, so we are sticking with this whole methodology of mixed design. The mechanistic empirical method of design is based on the mechanics of the materials that relates as input, such as wheel load, to an output, such as stress strain. Response values are used to predict distress based on laboratory tests and field performance. Dependence on the object. Observed performance is necessary because theory alone has not proven sufficient to design pavement successfully. And one of the reason how why we say impact mechanistic and empirical, in which what we do, we assume different, we assume some conventional thickness of the pavement, and then we calculate the stresses and strain. So the empirical, you use this conventional method, come up with thicknesses of the pavement, and then you input that in your model, mechanistic model, and then you find the answer. So this is what we call empirical mechanistic method. Use of vertical compressive strain of the surface or subgrade is a failure due to reduced permanent deformation, while some other scientists recommend use of horizontal tensile strain that I was talking about in the earlier part of this lecture. The use of above concept for pavement design was first presented in the United States by Dorman and Metcalf, 1965. How it works is that we limit the elastic strain to the subgrade and the elastic strain in other components above the subgrade. Hence, the magnitude of the permanent deformation on the pavement surface will also be controlled. These procedures are being incorporated by the Shell method, asphalt institute method. This is why we call this mechanistic empirical method. Researchers assume that mechanistic empirical design procedure will model a pavement more accurately than the empirical. The primary benefits that could result from successful application of the mechanistic empirical design procedures include ability to predict the occurrence of specific type of distresses, stress dependence of both the subgrade, the time and temperature dependence of the asphaltic layers. Now, what are specific type of distresses? It means to control fatigue, to control rutting, and there is another distress that is a low temperature cracking in the places where you have temperature most of the time in the year below 0 degrees centigrade. So that methods are also being used to design a pavement for or to verify the pavement against these distresses. Estimates of the consequences of new loading conditions can be evaluated. For example, the damaging effects of the increased loads, higher tire pressure, and multiple axles. Better utilization of available materials can be accomplished. Seasonal effects can be included in the performance estimates. One of the significant benefits is the ability to structurally analyze and extrapolate the predicted performance of virtually any flexible pavement designed for limited amounts of field or laboratory data. And this offers the potential to save time and money by initially eliminating from consideration those concepts that have been analyzed and are judged to have limit merit. Another point in adopting is that, stress strain of the material is not going from location to location. It doesn't vary, right? The climatic condition vary, the other things vary, but the stress strain response is more or less constant in different types. So that model can be applied to other parts. This is an advantage over the empirical method. These methods require more comprehensive and sophisticated data than typical empirical design. As we say, empirical design, it has, an easy approach, but the complex results. Here we have a complex result, complex approach, but a reliable results. So this is where the mechanistic empirical design procedures are heading to, and that's why it's preferred. Actually, work preferred. Now we have come up with this fully mechanistic methods, and there is AASHO 2002 model has been developed and is being applied in most of the, even it is not applied universally. Most of the countries are still trying to develop under their own conditions. But even in US, there are not many states that are practicing it. There are states that are practicing it. And again, the pavement design procedures are uh, the assessment type of this type of method is one one pavement life. For if some people have uh, developed this method in 2002, actually in 2002 they started developing. They have come up with a document around 2011. So in that place, if at 2011 someone has used this mechanistic design, and if it has designed for the pavement for 20 years, again 2031 they come up with their experience of having a mechanistic design pavement. It's too early to say, and it's and there will be process in which this method will be modified. So it's proven, but it's not proven for the practically, as I say. So it's still mechanistic design. Even in United States, it will take some time to get implemented fully. And when it gets implemented fully, then the country like our, will start thinking of it. So if you look at this, the pavement design, it comes around the triangle: thickness design, material design, construction practices, and quality control. One of the error lead to the failure of the pavement. You have very good material, you have got very good quality control, but your thickness design is not adequate. The result is the failure. You have adequately designed the pavement, the practice is very good, quality control, but there was error in your material selection, the pavement get failed. Or if you have both of this, thickness and material, under your control, but you cannot apply good quality control, then again the pavement is failed. So there are many ways a pavement can fail. Prematurely, before the pavement is going to fail anyhow, but if it is fails before its expected life, then we call this as a premature failure. The causes may be rutting, uncontrolled heavy axle loads, and limitation of pavement design procedures to meet local environmental conditions. And I'm talking about the context of Pakistan, and during the course of the lectures, I have also cited these reasons. These are the drawbacks of uh, pavements in Pakistan. One of the reasons is that, this. Let's go for this. This is one Pakistan truck, the load on one Pakistan truck, and for our standards, it is not that much loaded. What happens? So 18, sometimes 18 trucks is one Pakistan truck. Sometimes the 18 trucks that are used, the truck one, so 21 truck is equal to one Pakistan truck. So this is a loading of the truck damage. The damage caused by in US by 21 truck is actually the caused by one Pakistani truck. This is the state of affairs. The most of the problem in Pakistan is that rutting. So let's try to understand at which depth the rutting has occurred. The rutting can occur within the asphaltic layer. It means your thickness of an asphaltic layer is not adequately designed. And you can evident that if you have a straight profile, you will find some upheavals there. So this only happens where your asphalt layer fails. Then if you know there is a depression in the subgrade layer, then there is a problem either with your base material or the subgrade material. So this is it.